Okay, guys, today we're going to look at integration forms of inverse trigonometric functions. And to kind of jog our memories, in Bell work, I went back and had you find the derivatives of the inverse trigonometric functions. So the reality is we're looking at these forms to take the integral and go back to this form. Or you're looking at this form here to come back and get to like arctangent, arccotangent, and things like that. Please tell me, if you look at question 1 and question 2 on the Bell work, how are they different? That's it, right? The derivative form, negative is the arc cosine, the positive is the arc sine. Well, in integration, we don't know if I see something like this, if I know that came from the arc cosine, or if it just came from the negative of the arc sine as an original function. And so what we do in calculus is we actually only define 3 things instead of 6 items like we did in derivatives. So for instance, the integral of du over the square root of 1 minus u squared, and it doesn't matter if it's positive or if it's negative, will always just be the arc sine of u plus c. Now, does that match what's in the front of your book in terms of a formula?
Probably.
Or is there a little more symbology on it in the front of your book?
Yeah, this is a squared over minus u squared.
So they take us beyond this one, and I figured it would.
Arc sine of u over a.
Because it's du over square root of a squared minus u squared.
I thought they might have done that. So there we go. That's what we end up with. It doesn't matter if it's a negative or a positive. We only get that formula out of it. So obviously it's a negative problem, it's just negative the arc sine. That's it. So our challenge is going to be identify the pattern, identify this form, and then what is the a, what is the u? Let's get it figured out. We'll look at some examples in a minute. The second one that we've got here is the integral of du of a squared plus u squared. And so what is that going to be?
Arctangent.
Again, it's u over a plus c. Is that correct?
It has a 1 over a.
It has a 1 over a here?
Yes.
Okay. Again, there's only this formula. The 2 derivatives look very similar except for the positive and negative effect. That's the only one we get. We only use that formula. So don't try to go and get into the cotangent. We just don't want to deal with it. And then, last but not least, let's see, the integral of du over the absolute value of u times the square root of, is this one a squared minus u squared also?
U squared minus a squared.
Is it again a 1 over a times the arc secant
Of the absolute value of u over a.
That look right? Okay. Questions about this? So one of our goals is to match one of these forms. That's going to be our next challenge. The other problem you're going to notice really fast is some of the other forms that we've worked on in the past are going to look very, very similar. So we're going to have to be really, really particular about how these work. And as I go along, I want to kind of show you that a little bit as well. Is everybody ready for me to move on? So we want to take the integral of, well, let's do 5 over the square root of 4 minus x squared dx. And I want to compare that with the integral of 5 over the 5x over the square root of 4 minus x squared dx. I kind of want to know, are there similarities and differences, and are they the same answer or are they different answers? Now, as you approach both these problems, is there something we could do as a first step, without necessarily taking the integral just yet, just as a first step that maybe makes it easier for us to visualize?
Let u equal 4 minus 6 squared.
Maybe.
You could move the square root up, make it...
We could potentially do that as well, using the fractional exponents and moving the square root out of the denominator. But there's something a little more basic I want us to get an idea on, to say I really don't need this multiplier in the problem.
Yeah.
It's just going to be multiplying the answer as well.
The numerator, the constant in the numerator.
So we can take a look at the 5, and we can say, you know, this is the same thing as saying 5 times the integral of 1 over the square root of 4 minus x squared dx. Where down here, we can say it's 5 times the integral of x over the square root of 4 minus x squared dx. I know that's a subtle change, but does that help us visualize one of these and says one of these looks exactly like this arc something function? And if so, which one is it? How many think the one in black looks like the arc something function? A couple of you. How many think the one in blue looks like it? A couple of you. How many say, I'm not sure, probably one of them is, but I just don't know? There's one or two. I'm not getting much response. Some of you still on spring break, I guess.
5 arc sine of x over 2.
If you really look at your arc sine function, you're going to notice that we need to identify an a, and you need to identify a u squared, like an a squared and u squared out of here. And up here, it's just 1 or du. In this problem right here, if I let a equal 2 and let u equal x, does this match the pattern of this problem right here?
Yes.
Well, that's one good answer. Does everybody agree? Because in this part right here, then du is equal to dx, and we've got all those pieces. So we should be able to take this one and say this is equal to 5 times the arc sine of x over 2 plus c. Because that one matches the arc sine formula. How is the blue one different? We're afraid to talk, I think.
The numerator.
Somehow I stuck.
Yeah, it's the numerator.
That's different. If this one does not give me this answer, that x
If
makes
you
all the
let
difference.
Your u equal x still, you're going to get u over...
I actually don't let u be that entire denominator, other than the square root part. So what happens to this one as a du?
Negative 2x dx.
So this is going to account for that x as part of the problem.
Okay, so you don't use the new rule on it.
Because of that right there, correct?
Okay.
So we have to very closely match these up. That's what I need you to understand. This one works just great. This one does not match the same pattern, so we have to use a different technique. That's what makes this chapter so much harder, because I just kind of jumble them together on the test. So here you go. And you have to observe all the little details. We're going to finish this one in just a second, but you need to understand that this is what makes this one unique. If I choose this as my du, can I rewrite this problem so that it looks a little more familiar maybe? Somebody say yes. What does this problem rewrite to become?
Negative 5 over 2 integral of du over square root of.
Okay. Can we get away with u to the 1/2? Everybody okay with that?
Can you just make it u to the negative 1?
That's what the next step is. So now, if I take and integrate u to the negative 1/2 du, what is that integral?
Negative 5 the square root of 6 squared times 2.
So the integral of u to the negative 1/2 becomes u to the, and then we multiply it by the reciprocal of the power, plus c. We agree? Anybody have a problem with it? Okay. So negative 5 times the square root of 4 minus x squared plus c. Entirely different looking answer, entirely different valued answer than the previous problem.